You think you understand time because you carry a watch on your wrist. But that watch is telling you a comfortable lie. Time is not the rigid, universal metronome you've been taught to trust. It is flexible, relative, and far stranger than your everyday experience suggests. Most people assume time is the same everywhere, for everyone, always ticking at the same rate. This is fantasy. There is no cosmic clock. The rate at which time passes depends entirely on where you are and how you're moving. This isn't philosophy. This is measurable physics. Consider what happens when you accelerate. When you accelerate through space, you're changing your relationship to the quantum vacuum itself. The vacuum is not empty. What you call empty space is a seething ocean of quantum activity. Virtual particles pop into and out of existence constantly. The Casimir effect and Lamb shift confirm that the vacuum is alive with energy. When you accelerate, you don't see the same vacuum that someone at rest sees. This is the Unruh effect. An accelerating observer detects thermal radiation where an inertial observer sees nothing. You are bathed in warmth that exists only because you're accelerating. The vacuum is observer-dependent. Time and the quantum vacuum are intimately connected. When we write equations describing how fields evolve, time appears not as an external parameter, but as intrinsic to quantum structure. The propagators carrying information between space-time points encode both spatial and temporal relationships. You cannot separate them. In quantum field theory, we calculate probability amplitudes connecting events by summing over all possible paths, all possible histories. This is the path integral formulation. Time is woven into the fabric of quantum possibility. When you change reference frames or accelerate, you experience a different decomposition of reality into space and time. What one observer calls simultaneous, another calls sequential. The slicing of space-time into moments of now is not a feature of the universe. It is a feature of your perspective. Relativistic quantum field theory requires that all observers agree on experimental outcomes, regardless of their motion. This requirement, Lorentz invariance, forces us to treat time and space on equal footing. They are components of four-dimensional space-time. When you boost to a moving frame, space and time mix together. Your time direction becomes partly someone else's space direction. We've tested this with muons created when cosmic rays strike the upper atmosphere. A muon at rest decays in 2 microseconds. Classical physics says muons created 15 kilometers up should never reach the ground. But they do, because they're traveling near light speed. From our perspective, their clocks run slow. From the muons' perspective, the atmosphere is contracted. Both perspectives describe the same reality, using different time coordinates. There is no preferred frame of reference. Every inertial observer has an equally valid perspective on space-time. Your time is just as real as my time. General relativity reveals that gravity curves space-time. Time runs slower in gravitational fields. Atomic clocks at sea level run slower than clocks on mountaintops. GPS satellites must account for this. If they didn't correct for time running faster in orbit, your navigation would drift kilometers per day. The flexibility of time is in the technology you use daily. Place a clock near a black hole's event horizon. From far away, you'd see it slow down until it freezes at the horizon. But from the perspective of someone falling in, time passes normally. Two observers experience completely different durations for the same event. Neither is wrong. Quantum mechanics adds another layer. The Heisenberg uncertainty principle says we cannot simultaneously know both energy and the precise time with arbitrary precision. Energy and time are conjugate variables. The more precisely we pin down when something happens, the less precisely we can know its energy. When we calculate scattering amplitudes, we account for virtual processes occurring over timescales too short to measure. A photon can momentarily fluctuate into an electron-positron pair, then recombine. These virtual particles exist in quantum superposition, borrowing energy from the vacuum for instance, protected by uncertainty, yet their effects are real, contributing to the anomalous magnetic moment of the electron, measured to 10 decimal places in perfect agreement with theory. Time in quantum field theory is entangled with energy, probability, and causality. We work with proper time, the time measured by a clock moving along a particular world line. Different world lines experience different proper times for the same space-time interval. The path integral formulation integrates over all possible histories. The amplitude doesn't care about your clock convention. It only cares about space-time geometry and field configurations. Time is a label we assign, but the underlying physics is coordinate independent. The laws of physics don't depend on how we slice space-time into space and time. What matters are invariant quantities, things all observers agree on. The space-time interval between events, rest mass, electric charge. Time as you experience it is not invariant. It is frame-dependent, observer-dependent, flexible. If time is flexible, how can we preserve cause and effect? The answer lies in causal structure. Even though observers slice space-time differently, they agree on which events can influence which other events. The light cone structure protects causality. You cannot send signals faster than light. Even though time is relative, causal order remains consistent. Every clock has uncertainty. Every measurement of time has finite precision. To build a clock with precision, better than some interval, you need energy, greater than Planck's constant, divided by that interval. This is fundamental. The more precisely you measure time, the more energy you expend. There is irreducible fuzziness to temporal measurements. Despite these limitations, we do physics successfully because we've learned to think about time not as absolute background, but as a dynamical variable interacting with matter and energy. Time is not separate from the physical system. It is part of it. Newton assumed time flowed uniformly throughout the universe. This worked for his era, but at higher velocities, stronger gravitational fields, smaller scales, the Newtonian framework breaks down. Relativity and quantum mechanics require abandoning our intuitive notion of time as universal and absolute. In quantum field theory, we formulate physics through correlation functions describing how fields at one point correlate with fields at others. These encode all physics, constructed to be relativistically invariant, independent of any particular time coordinate. Time appears symmetrically with space. You cannot separate temporal evolution from spatial configuration. This unity of space and time is the most important lesson of 20th century physics. Time and space form a flexible, dynamical structure responding to matter and energy. Massive objects curve this structure. Observers, moving at different velocities, slice it differently, each equally valid. So abandon the idea of a cosmic clock ticking uniformly. There is no such clock. Every measurement of time is local, frame-dependent, and subject to quantum limitations. Time and space are components of unified space-time. How you divide space-time depends on your state of motion. The flexibility of time is fundamental, relevant from GPS satellites to black holes to quantum fluctuations. The mathematics is beautiful and experimentally confirmed to extraordinary precision. Quantum electrodynamics makes predictions accurate to 1 part in a billion. These predictions rely on treating time as flexible, on summing over quantum histories, on respecting space-time symmetries. For all this flexibility, there remains something absolute, the laws of physics themselves. They don't change from frame to frame. When we write equations of quantum field theory, we write them in manifestly covariant form. They look the same in all reference frames. This is the deeper invariance physics seeks. Time is more flexible than you think because it is not what you think it is. It is not an external parameter flowing independently. It is a coordinate depending on the observer's motion and position in space-time. When you check your watch, you're reading a device measuring proper time along your world line through curved space-time, fundamentally limited by quantum mechanics. This is cause for wonder. The universe is far more subtle than everyday experience suggests. Time is deeply strange, wonderfully flexible, and intimately tied to space-time geometry and quantum structure. Your intuition about time was formed by evolution for survival in a world of slow speeds and weak gravity. The goal of physics is not to confirm intuitions, but to reveal reality's structure, even when that contradicts immediate experience. Time is flexible, space-time is curved, the vacuum seethes with quantum activity, and this fits together in a mathematically consistent framework, making testable predictions. So when you glance at your watch, remember, you're not seeing time itself. You're seeing one device's measurement of proper time along one world line through curved, dynamical quantum space-time. Time is so much more than you think. And that's exactly what makes it worth studying. Thank you all for listening, and don't forget to like and subscribe for more.